On December 19th, at observatories around the globe, every massive radio dish will lock onto a single icy traveler, the third interstellar object ever found, 3I Atlas. If we hear only cosmic noise, it is another rock. If we catch a narrow signal, everything we know about life in the universe explodes. The odds are tiny. But what if, just once, the silence breaks? When the Minor Planet Center issued the designation 3, I for C 2025 N1 Atlas on July 2, 2025, it joined a list that barely exists. Only two other objects, Oumuamua and Borisov, have ever been confirmed as interstellar visitors. The odds of spotting one are so low that astronomers expect to wait decades between discoveries. But 3. I Atlas refused to be ignored from the start. It was first spotted by the Atlas survey on July 1, 2025, just days after it slipped out from behind the dense star fields near the galactic center. Its trajectory told the story, a hyperbolic path moving too fast to be bound by the sun, destined to pass through and vanish forever. But rarity alone did not trigger the global scramble. What set 3I Atlas apart was its behavior. Even at 6.4 astronomical units from the sun, well beyond Jupiter's orbit, it was already active and bright. Data from the TESS Space Telescope, gathered between May and June 2025, captured this early outgassing. Most comets wait until they are much closer before sunlight can thaw their ices. But 3I Atlas was shedding material in the deep cold. That kind of activity suggests extremely volatile ices, possibly carbon monoxide or carbon dioxide, chemistry that hints at a very different birthplace. Observatories rushed to gather every possible measurement. JWST locked on with NIR spec in August. Hubble turned its ultraviolet spectrograph toward the object in November. The Rubin Observatory caught it during a rare window in late June and early July, helping to pin down its size and coma. By December, 3I Atlas was moving through Virgo and Leo, fading fast but still under intense scrutiny. Every dataset sharpened the mystery, steady brightness, no wild outbursts, and a compact coma that defied easy explanation. For astronomers, the combination was irresistible. An object from another star system, active at a distance where most comets sleep, and bright enough to trigger a worldwide, multi-wavelength chase. The scientific playbook changed overnight. If there was ever a candidate worth listening to, not just watching, this was it. A radio telescope is not just a giant dish pointed at the sky, it is a machine built for precision, designed to catch the faintest whispers from the cosmos. The Green Bank telescope, with its 100-meter-wide parabolic surface, focuses radio waves onto a single receiver no larger than a coffee mug. Every photon that strikes the dish surface is directed, concentrated, and measured. The process begins at the edge of the atmosphere and ends deep inside racks of electronics, amplifiers, digitizers, and computers, humming with anticipation. When a target like 3I Atlas sweeps across the sky, the challenge is to keep the telescope locked on its predicted path. The Deep Space Network, with complexes in California, Spain, and Australia, is built for exactly this kind of work. Its antennas can track moving objects across the sky with sub-arc-second accuracy, relaying position and timing information in real time. This network does not just support spacecraft, it provides the backbone for any global campaign that depends on knowing exactly where to point and when. At Green Bank, the signal chain is relentless. Incoming radio waves traveling for millions of years are converted from analog to digital in fractions of a second. The data rate is staggering. Terabytes per hour stream into high-performance computers, where software splits the signal into thousands of frequency channels. Each channel is analyzed for patterns, spikes, or drifts that might hint at something more than random noise. The sheer volume of data means that automated systems handle the first pass, flagging anything unusual for human review. Coordination is essential. As 3I Atlas moves, its position is handed off from one facility to another. When the object sets at Green Bank, it rises for the Deep Space Network in Madrid or Canberra. This choreography ensures there are no gaps in coverage, no missed opportunities if something unexpected appears. Each observatory's data pipeline is tuned for sensitivity, able to stare at a single patch of sky for hours, searching for the faintest sign of order amid the static. The goal is simple. If a signal is there, no matter how brief or faint, the system must catch it. Every byte, every spectrum, every second of listening is a chance to capture something that has never been heard before. Natural radio emission from a comet is anything but tidy. At the frequencies searched by radio telescopes, a typical comet produces a restless blend of signals. The baseline is thermal radiation, a broad, low-level hum that stretches across a wide range of frequencies, shaped by the dust and icy nucleus as they absorb and re-emit energy. Layered on top are molecular lines, the fingerprints of gases like hydroxyl, water, and carbon monoxide. These lines are never razor-sharp. Instead, they spread out, often spanning kilohertz to megahertz, broadened by the speeds of outflowing gas and the comet's own rotation. This is messy. The profile is unruly. Outgassing jets flare and fade, sometimes spiking the radio spectrum with irregular bursts. As the nucleus spins, different active regions sweep in and out of sunlight, modulating the emission in unpredictable ways. Even the strongest lines, like the OH transition at 18 centimeters, appear as smeared asymmetric features, not the crisp spikes of a transmitter. This is the expected chaos. Every natural comet, whether local or interstellar, generates a radio signature defined by noise that fills the spectrum, lines that wobble and blur, and flares that refuse to repeat on command. It is a world of random static, not order. For astronomers, this confusion is the default. Anything else demands a second look. A suspicious spike in the data sets off a chain reaction. The first filter is brutal. Only signals narrower than 1 Hz, with a clean, unbroken line, even make it past the automated gatekeeper. Turbo SETI, the software backbone for Breakthrough Listen, flags these outliers in real time, scanning for the telltale signature, a razor-thin frequency drifting steadily in a way that matches the comet's motion, not Earth's. Drifting is key. A real transmitter riding on 3I Atlas would show a linear change in frequency matching the object's predicted acceleration across the sky. Anything that jumps, jitters, or hops gets dumped with the rest of the radio trash. But even a perfect candidate is guilty until proven innocent. The next step is the radio frequency interference mask. It is a living map of every known satellite, aircraft, and ground transmitter. If the signal matches a frequency used by Starlink, GPS, or a passing radar, it is out. The pipeline cross-checks against NORAD satellite catalogs and local interference logs, hunting for any match that could explain the blip. Only when a signal survives this gauntlet does it escalate to human review. Seth Shostak says no one trusts a single dish or a single night. Andrew Simeon outlines the protocol. Within hours, teams at Green Bank, the ATA, and overseas partners scramble to confirm or refute the candidate. If it is real, it must reappear at another site, on the same frequency, with the same drift. History remembers the hard lessons. The WOW signal never repeated. BLC1 collapsed under cross-checks. Now every candidate faces a 24 to 72-hour window of relentless scrutiny. The clock runs, and the world waits in poised uncertainty. Right now, thousands of worlds drift past us, each a cosmic message in a bottle, most silent, a few still unknown. As technology sharpens our listening, the universe grows less indifferent. The next signal could redefine what it means to be alone. Stay curious. The silence isn't final.